Alright, to do this problem you need to differentiate this equation explicitly. So we'll take the derivative with respect to x of both sides of the equation, and we'll get 2y then times dy dx plus, and then this is going to be 3 times xy plus 1 squared, but then times the derivative of the inside. And the derivative of that inside is going to be x times dy dx plus y times the derivative of x, which is just going to be y times 1, equals, and the derivative of the right side, of course, is 0. Then what I would do is I would not try to solve for dy dx. Instead, I would plug in what we know here. We know x equals 2 and y equals negative 1. And if we do that, we get 2 times negative 1 times y prime plus 3 times 2 times negative 1 is negative 2 plus 1 quantity squared, and then times 2 times y prime minus 1 or plus negative 1. And that's going to be negative 2y prime plus 3 times, that's going to be negative 1 squared, which is just 1, and then times 2y prime minus 1 equals 0. And let's see, negative 2y prime plus 6y prime minus 3 equals 0. So that, if you solve that for y prime, you get that y prime equals 3/4. And that is choice D. Alright, some partial fractions here. So the bottom of that fraction there factors to x minus 4 times x minus 2. So I can think of this thing as 1 over x minus 4, x minus 2 is equal to a over x minus 4 plus b over x minus 2. And if I clear the fractions, I get 1 is equal to a times x minus 2 plus b times x minus 4. And if I am clever with what I plug in, I can plug in x equals 2, and if I do that, I get a equals b times negative 2, so b equals negative 1/2. And if I plug in 4 for x, I get 1 equals 2a, so a is equal to 1/2. So, knowing that, I can then say that this integral will be the same thing as a, which is 1/2 times 1 over x minus 4, and then minus 1/2 times 1 over x minus 2. If I integrate that, I get 1/2 the natural log of the absolute value of x minus 4, and then minus 1/2 the natural log of the absolute value of x minus 2. And then I look at these, since it's being subtracted, I look at these properties here. I could factor out a 1/2, and I'll have natural log of x minus 4 minus the natural log of x minus 2, and one natural log minus another natural log is the natural log of the quotient of the two arguments. So it is choice A on that one. Alright, so this one is using the chain rule. A couple times chain rule, product rule. So we'll start out with just take this thing here and take its derivative. So h prime is equal to, well, it's going to be f prime of g times g prime. Alright, there's my first derivative. My second derivative, I now have to use the product rule. So h double prime is going to be, well, it's going to be f prime of g times g double prime, plus, and then it'll be g prime times the derivative of this guy here, which is going to be f double prime of g, and then times the derivative of that inside, which is g prime. And if we simplify it a bit, what you'll see here is this combines to these g prime times g prime is going to be g prime squared times f prime. And if you look at the first thing here, you've got f prime of g times g prime. So it is times g double prime. It is choice A again here. So if you do a little simplification, you can see here that this is the same thing. So you can use shorthand just as long as you don't have to write the of x every time, because they're all of x. So shorthand is good. Yeah, and this one here is if you forget the product rule. You don't want that one. This one's here, so you have no idea what the chain rule. And this is, I'm not sure, a little bit of chain rule, definitely no product rule. It's just product rule, but I'm not sure what they did there. Something. Alright, so there's two ways to do this problem. One way is to look at this differential equation and then just kind of eyeball its antiderivative. So you look at this and you say, well, if y prime equals that, then, well, I could kind of, it's hard to do u substitution because you don't, well, you could say, actually, you could do dy is equal to cosine squared of x times the sine of x dx. I guess you could integrate both sides. You could also kind of eyeball it here, so you get y is equal to, what's going to happen here? Well, if you were to let u equal the cos of x, then du is going to equal negative sine of x plus c. So if you do that, then you'll get y is equal to, and if you plug that in, this becomes negative u squared du, so you'll get negative 1/3 u cubed, and what's u? U is cosine of x cubed plus c. You could totally get this by eyeballing this if you wanted to as well. And then what do we know? Well, we know that this is true. So if you plug in pi over 2 for x, you'll get y equals 0. So that means that 0 is equal to negative 1/3 times the cosine of pi over 2, which is 0, and then plus c, so c must be 0. Oh, that's really nice. So this just kind of goes away. I've got this function here, and I want to know when I plug in 0, when x equals 0, what's y? Well, you'll get the cosine of 0 here, which is 1, and negative 1/3 times 1 is negative 1/3. So there is your answer. Okay, so another way of doing this problem is to think of an integral, because we basically have y prime. And you could think about the y prime dx integrated from x equals 0 to x equals pi over 2 is going to equal, it's going to equal y of pi over 2 minus y of 0. Now, it's really bad handwriting there. Okay, and then you can evaluate this integral. And to do this integral, well, you do from 0 to pi over 2 of the sine of x cosine squared of x dx. And if you do some u substitution, you let u equal the cos of x. Then what this integral will turn into is the integral from, well, the bounds you'll have to change, so this will be from 1 to 0, because again, u is equal to cosine of x, cosine of 0 is 1, cosine of pi over 2 is 0, and then you'll have negative 1/3 u cubed du. And what that's going to be then is, when you do this all out, you're going to get 1/3. And so this is equal to 1/3, but we also know that this part here is 0, so negative y of 0 is equal to 1/3, so y of 0 must be negative 1/3. All right, so the key on this problem is to realize that it says that f is a linear function. So that means that f of x, I don't know, is something like ax plus b. That means that f prime is equal to a, which means that f double prime is equal to 0. Of course, yeah, the second derivative of a linear function is going to be 0 because there's no concavity. So now what I'm doing is I am going to then integrate f double prime of x, which is 0 dx from a to b. And if you do that, well, what happens? Well, the antiderivative of 0 is some constant evaluated from a to b. Well, constant evaluated at b is going to be a constant minus a constant evaluated at a, and that's also a constant. And constant minus the same constant is 0, so that is 0. Yeah, and the other way of thinking about it is this right here, you're finding the area under the curve, y equals 0 from a to b, and that's going to have no area under that one. So for 11, the answer is A. Alright, so here's a function. They want us to find the x-coordinates of all points of inflection. And so you guys hope all know that you want to look for a second derivative. So let's do that. So if we look at, whoa, wrong pen there. So f prime is equal to, well, the first derivative is going to be 15x to the fourth minus 20x cubed, and the second derivative is going to be 60x cubed minus 60x squared. And if we take out a 60x squared, we end up with 60x squared times x minus 1. Okay, so this is going to have two zeros, one at x equals 0 and one at x equals 1. But the key thing to know here is don't just go here, because you see 0 and 1, you're like, nice. Well, don't do that, okay? Because in order to be a point of inflection, the concavity has to change. It has to switch from concave up to concave down, or concave down to concave up, which means the sign of the second derivative must change. And because x is being squared here, it is a bounce on the graph, so it actually does not switch concavity there. So there's only one place where it switches concavity, and that is at x equals 1. And that is your one and only answer for number 16. And that is one that fooled a lot of people, because only about half the people that got 5s got that question right. So hopefully you didn't fall for the sucker answer, which was D. Alright, so I might have put this question on a test that I gave you guys earlier this year. I can't remember. But it is talking about what is going on at 1. What is f of 1, f prime of 1, and f double prime of 1. And the key thing is to look at this graph and say, okay, what's going on there? Well, the function is, f of 1 is 0. The function's increasing at 1, and it's concave down at 1. So, well, f of 1 we know is 0. And if the function's increasing at 1, then I know that f prime of 1 is greater than 0. And then if it's concave down at x equals 1, then I know that the second derivative is less than 0. So if I wanted to order these, the second derivative is going to be the smallest. So this is the smallest, and this is the second smallest, and that's the third smallest, so it must go f double prime is less than f prime, and there we go. So for 17, D is the answer. One, which of the following series converge, and you have to get all three right in order to get this one. Well, let's see. Well, the first one is going to, well, if you look at it and you say, okay, if n goes to infinity, what happens here? Well, this whole thing goes to 1. So eventually you're just adding 1 plus 1 plus 1 plus 1, and that's no good. This one, the part 3, I'll come back to the number 2. Part number 3, you're like, wait a minute, that is I should know that one. That's got a name, that series. That is P series, where P equals 1. What's that called? Oh, it's the harmonic series. And the harmonic series famously diverges. So you could do that by P series test. P would be 1, and 1 is not greater than 1. So that doesn't work. So that's no good. So now we're down to two possibilities, either A or B. And the question is, does this guy converge? And this one's, we had a, I think on the quiz I gave one similar to this, but if you start looking at some values, you plug in some values. So when n equals 1, what happens? Well, at n equals 1, you get cosine of pi, which is negative 1, over 1. And if you plug in n equals 2, well, you're going to get cosine of 2 pi, which is 1 over 2. When n equals 3, you're going to have cosine of 3 pi, which is going to be negative 1 over 3. And then if n equals 4, you're going to have cosine of 4 pi, which is back to 1 over 4. Oh, and look at this. This is a harmonic series, but it is alternating. And yeah, so really this is the same series as negative 1 to the n over n, from n equals 1 to infinity. And that's the alternating harmonic series, and it definitely converges because each term is getting smaller. They're going to 0. And actually, I think we proved at some point that this actually converges to, in this case, I think it'll be negative natural log of 2, I think. Yeah, something like that. Anyway, you don't need to know what it converges to, but it does converge. All right, so for this one, the rate at which, when x equals 8, the rate at which cube root of x is increasing is 1 over k times the rate at which x is increasing. So the way I thought about it was I thought about writing an equation here that y is equal to cube root of x, or x to the 1/3. And what you can do is take the derivative of this with respect to time. And if you do that, you get dy dt is equal to 1/3 x to the negative 2/3 times dx dt. But they told me that the rate at which y, well, y in this case is cube root of x, the rate at which, and so that's really the rate at which dy, basically that's saying that dy dt, this is all you can think of this, the rate at which this is changing is dy dt. So dy dt is 1 over k times dx dt. So I can say that dy dt is equal to 1 over k times dx dt. And the nice thing about that is I can then sub that in. And I'll have 1 over k times dx dt. Sub that in for y, and that's going to be 1/3, and I could put this down here and say x to the 2/3 times dx dt. And dx dt we know is non-zero, so I can actually divide both sides by dx dt. And so I'll get 1 over k is equal to 1 over 3x to the 2/3, and we want to find it at x equals 8, and if I plug that in, I get 1 over k equals 1 over 3 times 8 to the 2/3, which is 4. So I'll get 1 over k equals 1/12, so k must be 12. What is the mean value theorem? That is what this is saying. It's just testing you straight up. Do you know the mean value theorem? So let's see. There is a continuous, let f be a function defined and continuous in the closed interval a to b. If f has a relative maximum at c, which of the following must be true. Okay, well, they never said it had to be differentiable. Okay, so it's possible, well, it's possible that if it has a relative max there, then it goes up and goes down. But it could also go from from A to B. It could also go boom, boom. So I do not believe that f prime needs to exist. But if it exists, the derivative is 0. I think so. I think that's right. So if it's actually differentiable there, and it's a max, the slope better be equal to 0. And then, this is saying that if f double prime exists, then the function's concave down. Yeah. Yeah, seems like if it's concave, if it's a max, it's going to be concave down. So I think we can say safely that it is 2 and 3. All right, so we've got an improper integral here, and we can do this one either by eyeballing it or by hand, or by u substitution. I'm going to do u substitution just to get a little practice that way. So I'll let u equal negative x cubed. And the key, I guess, is to take a look at it and realize that if this is your u, this exponent is your u, its derivative is negative 3x squared. So that's where this x squared came from. But if we start playing around with this, then if u equals negative x cubed, then du dx is equal to negative 3x squared. That means that dx is equal to negative, dx is going to be du over negative 3x squared. And when we plug this all in, we're going to get the integral of x squared times e to the u times du over negative 3x squared. And so I'm going to get negative 1/3 the integral of e to the u du. And then it's going to be evaluated from where to where. Well, if x equals 0, y will be 0. Excuse me, u will be 0. And if x is infinity, then u will be negative infinity. And so if I anti-differentiate this now, go up here, I guess, I'll get negative 1/3 times e to the u, evaluate it from 0 to negative infinity. And if I evaluate it at negative infinity, I'm going to have negative 1/3 times e to the negative infinity, which is going to be 0, and I'll have minus e to 0, which is 1. So it's going to be negative 1 times negative 1/3, and that's going to be, so negative 1/3 times negative 1, and you can't really read this, sorry, and that's going to be positive 1/3. And it makes sense it has to be positive, because if x is positive, this is always positive. So this actually, you could totally use Earl Fry here, because that can't be true. But it's weird that they picked 1/3 twice. This integral has to be positive. That function's always greater than 0 on the interval. Actually, for all x except for 0, that thing's 0. So there's no way you could get that unless you're going backwards. So anyway, 25 is C. All right, nice. A logistic function. Yes, you should recognize this as logistic. Looking at this differential equation here, it is a quadratic as a function of p. There are going to be two different asymptotes here for p. So if I were to do a quick little graph, I'd have some axes here. And what do I know? Well, the slope is 0 when p equals 0. And the slope is also 0 when p equals, well, when this part here equals 2, and that's going to happen at 10,000. And actually, if I've thought about that much, then I've already kind of got my answer. It's got to be 10,000. But if we want to look at what this graph had to be, it's like, well, this is going to be at 10,000 here. And the slope is 0 there. It's also down here. In between, if I plugged in like 100, this is all going to be positive. So it's going to have a positive slope. It's going to go something like this. And this is at 3,000 here. Yeah, this is going to have to be something like that. And we do know that halfway between here at 5,000 is when it's growing the quickest, which is another common problem, and which they put on there as a possible answer, but that is not right. that's saying, that's when it's growing the quickest, but they want to know what is p as t goes to infinity. So that out here, as t goes to infinity, this thing's getting closer and closer to 10,000. So that is your answer. All right, so you are told that Taylor series converges to f of x for all x. What's f prime of 1? Well, there's a couple ways of doing this. One is just to write a couple terms of it, and things will, I think, come out kind of clear. So f of x is equal to, well, the zeroth term is going to be a sub 0, x to the 0, and then you're going to have a sub 1, x to the first, and you're going to have a sub 2, x squared, plus a sub 3, x cubed, plus dot, dot, dot. And if I'm going to take a derivative of this thing, I'm going to have f prime is equal to, well, this is times 1. So this is just a constant. That's going to go away. So that's going to become 0 plus a prime plus 2a squared x plus 3a sub 2. Did I say a squared? 2a sub 2x, and then it's going to be 2a sub 3 x squared plus dot, dot, dot. So what's going to happen here? Well, you're going to have, well, let's see, things have dropped down, and you're going to have these a sub numbers. We got some options here. Well, there's a there's going to be, oh, we want to plug in 1. So if we plug in 1, sorry, I forgot about that part. So f prime of 1 is going to be a sub 1 plus 2a sub 2 plus 3a sub 3. That's easy enough to see, and this is, I guess, 1a sub 1. So it's going to be this guy right here, D. 27 is D. Sorry, I was going to make it more complicated for a second there. All right, let's take a look at this limit. Well, if you start thinking about it and you look at the top and you're like, well, if I'm going to 1, what is going on here? Well, this top here, you'll be doing the integral from 1 to 1 of that function. Well, if you go from 1 to 1, you are going to get 0 over, and at the bottom you're going to get 1 minus 1, which is 0. So you get 0 over 0. Ooh. Which means, it means we can use something called the L'Hopital's. Good old L'Hopital's. So what do we do to use L'Hopital's? Well, we take the derivative of the top and the derivative of the bottom separately. And if the derivative of the top, well, if you're going from 1 to x of e to the t squared, well, you take the derivative of that with respect to x, and you're just going to get e to the x squared. Over, and the bottom is going to, if you take the derivative there, 2x. And then we look at the limit as x goes to 1. And up top, we're going to get now e to the first squared. And so e to the first over 2. So there it is. 28 is C. And 28, yeah, there it is.